You know, is our section is named Geoinformation database for mega cities and new capitals, and the Geoinformation database for mega structures and some unicum buildings and also historical buildings, every interesting situation, soil structure interactions. So, you know, I am representative of Kazakhstan Geotechnical Society, also representative of Russian Geotechnical Society. And today is the first presentations will be make Professor Ын Чуль Шин here. Professor Ын Чуль Шин. So I want to introduce Professor Ын Чуль Шин. So Professor Ын Чуль Шин is Vice President of International Society of Soil Mechanics and Geotechnical Engineering. Also full professor of Incheon National University. Also president of private company Korea Consulting Company. He opened, I think, is 1 month ago or 2 months ago. Is I congratulation is new way for developing of second life of Professor Ын Чуль Шин. And also Professor Ын Чуль Шин graduated in the Korea, related with bachelor and master program, and PhD he received in the US. So his presentation will be related to his constructions of social infrastructure for reclamation soil ground of free economical zone on Sonda. So please, Professor Ын Чуль Шин. Так, можно, да, вот экраном хочешь показать, это где нужно нажать? Да? Да. Так. Так. Все, вот это можно закрыть, вот это?
Ну да, это чат можете закрыть.
Так.
Демонстрацию красную.
Остановить, да?
Да, это потом.
Сейчас?
Нет, не надо. Когда вы закончите. Все, демонстрация есть.
И что, да, где вот эта деформация? Демонстрация?
Да. Это показывается
вот смотри, пока не будет, его будет показывать, его демонстрацию, я вот хотел...
его демонстрацию?
Да, его. А моя демонстрация у вас есть?
Все, не надо, тогда пускай он включает демонстрацию.
Да. Это, да. So, Professor Ын Чуль Шин, can you make demonstration your presentation? Professor Шин. Что-то он не слышит меня, что ли? Вот смотри.
Professor Askar, you can ask any other. Okay, now he is completing.
Come?
Yeah.
Это вот включил, просто не включает, наверное. Professor, yes. you can put your presentation now, Professor Шин.
Just for trial.
Вот, все. Так, вот смотри. Вот я хотел отсюда мою презентацию записать. Или, может быть, я отправлю вам ее? Не надо?
So I can go ahead, okay?
Yes, you're beginning, yes.
Thank you very much, Professor Askar, for your kind introduction. The topic of my presentation today, construction of social infrastructures for Songdo Free Economic Zone in Korea, which is located in Incheon, where our university is located. And I'll briefly introduce the background of this paper and soil condition and the ground improvement work and our construction and conclusion will be given. Okay, so the Moscow is about about the 10 hours of flight, but we have 6 hours different. Our the Korea
Записан, да, уже?
Far East,
Здесь будете.
very small country, compared with Russia. Russia is a big continent, but South Korea, here small. North Korea is here. They have a big nuclear bomb. We need help from the Russian, the government to stop his, treating. And this is a panoramic view of the Songdo, Incheon. All this land declined from the sea. This is a man-made land. We have many beautiful, structures and the park around this area. And we have a lot of greenery. And of course, we have metro lines underground here. And this is POSCO company, our university located in the right-hand side. And we have a big golf course. And here there's Incheon International Airport, also they constructed on the man-made land. And also we have Songdo is right here, this area. Used to be a sea, but now we made a land and for the construction of the infrastructures. And we have the criteria of the soft ground here. And all this land, all this area, this airport area, and the Songdo area I'm talking about here, all man-made land, and we had a lot of ground improvement work, which was begin in the 1992, 1994, in the past 26 years. And we reclaim the land from the sea, like here. Now we have a very big dredging ship, which is working now the midwestern part of Korean Peninsula. We have a Saemangum area. We have some consultancy work for this area. We have a lot of settlement problem like this in land. And this is a dredging pipe to put in the dredging soil into the inside the dike. And also we have a lot of soils strata in the horizontal sand range, so which could help to have the efficiently ground improvement with the corporate of the vertical drains, some piles and so on. Then we have soil stratification like this, on the top of the reclaimed and the silty clay, sand, whether the rock and the soil, and we have another cross section. We have all these soil properties, or we have a database on here, like Professor Yoshinori has in the Osaka area. This is a pretty much normally consolidated clay, so it's a pretty stable condition. It's not expensive, not very high, the clay content here. So we have various ground improvement the work, deep cement mixing, geotube, and sand compaction pile, and the special foundation system, pitch pile, and the point foundation system, and so on. Here we have a PH pile, the high strength concrete pile, for the foundation of this northeast trading, that building, and we have a kind of body pile, this is the United Nations building, the G Tower we call, and like this. Because we are constructing in the middle of the city, so we don't have any driving pile. We have a pre-board, and we install this and cement, the gravity. And we have an anchoring system here, and furthermore, we have a lot of common utility box underground. So this is the water main, and this is maybe hot water heating pipe, and this is electric cable is underground. So we have all this facility underground, so we cannot see any electric post above ground, and we have many CCTV camera, so we can surveillance any damage, any problem underground. So we monitoring this lifeline facility 24 hours a day. So this is and also we have several sand compaction pile, prefabricated vertical drain, ground improvement work this area, and we ground improved, and also we have a geosynthetic clay liner at the bottom of this canal, this man-made canal. And on the top, we have like a geocell. So we made an artificial slope for this particular Central Park area. This is a concert hall. And we have a pretty good, the shopping mall here and there, and also the international schools. And in those areas, we ground improved by the sand compaction pile. And many years ago, about 30 years ago, we learned this technology from the Japan. And you see that diameter about 60 to 80 centimeter with the spacing about 1.8, 1.5, 2.0 meters. And the depth of this ground improvement around here about 18.5 meters average. Okay, this is a equipment and monitoring the graph. And also we did use a lot of prefabricated vertical drain because of the lack of sand, because this LOC, in here we have a silty sand, so not much good gradation of the sand for sand compaction pile. So we use the prefabricated vertical drain and lateral, and also we did use this deep cement mixing method for the like jet crouching work, and under the station of the metro, and also triple or RJP and also JSP we do use a lot for this area. This is the layout of the RJP. I think a triple the pole for this equipment, and this is a deep mixing machine along behind our university. Just prior to the construction of the sea dike, and we want to ground improve at the bottom of the soft, the soft clay at the seabed, and also we have a lot of deep DCM application here. We checking the elasticity modulus, but with curing days as here we have very much improved by 28 days, and also dynamic compaction we have, and the deep dynamic compaction and also shallow dynamic compaction. This is convention hall in Songdo, and this is a shallow dynamic compaction for the road, because deep dynamic compaction has a problem, too much vibrating and noisy. And here we have about ground improvement of 5 meter depth, okay, by the shallow ground improvement method. We have a point foundation along the international university campus here. We have here very simple this equipment, but we have here this kind of foundation. This is tip and then this is the top. Okay, so the here and the bearing we normally we just stand the penetration and value about 15 to 20 blows in those areas. Now we do pilot test over here to see the bearing capacity of this. I think this would be very good for the foundation for the soft ground in the parking lot, and also the middle, high, low, the apartment complex and residential area. We have 3 5-story buildings. This is a high strength concrete pile foundation. This is a soil cement column foundation. And this is a basal foundation, system. So 3 different, but different foundation system. I think this is a basal foundation. The system has a little problem during this underground excavation work. But during this pile driving, we have a problem here too. So we did use the both pile, situation. This is a basal foundation. Sometimes there's a problem. This one, and that's conical foundation because the water, dissipating during the construction on Jason, structure, underground construction, it has a problem. And we did use the geotextile tube for the temporary dike for this, bridge construction work for the bridge pier and all these. Used to be we used the sheet of pile to make a temporary dike, but use the geotextile tube in this case and 3 layers. And we monitoring for this, and we calculate the stability and the sliding, overturning, and the bearing capacity. And this is the process of the construction work, airframe mat and setting, and we pumping the slurry sand into here like this. It's not very difficult. And here we have a twin tube, and on the top we have a mattress, and the cement milk we injected and make a flat form of the second layer. And this is very successfully implemented and monitoring all the vertical stress and the port pressure dissipation with the different layers. And we did use the mammoth compaction pile and also did the soil mixing method and cement grouted this to send the compaction pile on the sea, and this is monitoring, and also this is the deep cement mixing at the bottom of the sea dike, and we'll have a secondary perimeter highway will be constructed around the metropolitan area, and this is a method of the construction work. And we have two injection holes, bottom and top. And when you're driving, we have injection from the bottom, but when you withdraw, we have the injection, the cement grout from the hole on the top. Okay, that's very efficient. And see that this is a lift up injection, and this is a very good and a higher unconfined compression strength compared with the penetration injection. Okay, and the curing days of 28 days, and we presented the various of the soil ground improvement method, and I think so we pretty much the confidence and the cost effective of this method for social infrastructure in Songdo area, and I think this is about all and the presentation. Thank you very much for your pay attention. Thank you, Askar.
Thank you very much, Professor Shin, for interesting presentations. So maybe some questions. So I will inform. So each lecture now is we have some make copy for YouTube, and this your lecture will be distributed for this forum, members of forum. But anyway, maybe some questions from our speakers and from maybe some participants also, please.
Professor Askar, I have a question.
Please, Professor Bumi, not Han.
Yeah. Professor Shin, you made a very interesting presentation. You covered all ground improvement techniques. I have a question specifically, how popular pile foundation in South Korea compared to ground improvement methods?
Pile foundation?
Yeah.
Oh, we have a pile foundation pitch pile.
Particularly for heavily loaded building, heavily loaded structures.
I'll show you the. See that we have a main contractor, right? Like the yes. Then they give the subcontract. Okay? So they have some company. They specialize. They have machines and also they have technology to do this. Okay, so we have a special contractor. Okay, so the Korean company, they're working for this project. So whenever we have a project, we need special the subcontractor. They carry out the work. Okay.
Okay. One more question.
Yeah, we have a ground.
Particularly when we have pile foundations in soft clays.
Yes,
how do you increase the lateral capacity?
Yeah. Here, normally in the South Korea, we have the depth of the weathered rock. It's not very deep.
Okay.
We have about 15 meters and maybe 10 meters, and this coastal area here, particular area, we have about 28 meters depth. Okay, so all the pile is rested on the bedrock. Okay, so it's a very reliable. Not like Japan, not like Vietnam. Vietnam has maybe the soft soil depth of about 60 or 100 meters. Immensity, it's very difficult. But we have a very confidence here because all the pile foundation rested on the rock. Okay, so.
Thank you, Professor Shin.
Thank you for interesting questions and also very good reply. Any questions? So thank you very much, Professor Shin. I congratulate you again with opening Korea consulting company. So I hope you will be develop your knowledge and transform your knowledge to real practice in Korea. Not only Korea, maybe even also Kazakhstan and Japan, in India as well.
Like this, the box facility for you know the big new city. Okay, thank you.
So thank you. So next our presenter, Professor Adimulam Buminatan. So Professor Bumинатан is full professor of geotechnical division of Faculty of Civil Engineering of Indian Institute of Technology, Chennai, India. So he also chair of branch of Indian Geotechnical Society in Chennai area, and also he is one of big specialists of piling foundations and numerical analysis, and also site investigations, and also he has many projects now, especially related to his from grant of government of India. So his presentations will be related with some estimations of territory of Chennai city by special wave of surface. Please, Professor Bumi.
The slides are visible?
Yes, yes. Very good.
Okay.
Very good.
Okay.
Perfect, perfect.
Thank you, Professor Askar, for a kind introduction and as well as giving me an opportunity to give a presentation on the topic of surface wave method based site characterization for typical sites in Chennai. As the professor told that I belong to Indian Institute of Technology, Madras. My co-authors, my student, previous PhD student, Dr. Jania, as well as current PhD student, Kritika. You know that in India, it's basically a lot of infrastructure facilities are coming out like South Korea. And we have to know more detail about the site profiling as well as soil properties. Conventionally, we are doing borehole drilling actually. But particularly when you have large projects, drilling boreholes takes time. And sometimes between the borehole also, we may miss some important information actually. So therefore, currently, our institute actually, IIT Madras, involved carrying out the surface wave test, especially in building projects, needed to confirm the profile obtained from the borehole data, as well as it is basically giving additional information about the two-dimensional soil profiles actually. So basically, my presentation mainly covers some of the carried out on typical sites in Chennai. Just initially, you may know some of you, just to introduce what do you mean the principle of surface wave method actually. So our soil medium is an elastic half phase actually. When the velocity of this, when surface wave propagates, surface mean mainly here we are talking about Rayleigh wave actually, R waves actually. It depends on the velocity, depends on the frequency or wavelength of the wave actually. This relationship between the frequency and waves velocity is what you call the dispersion curve actually. So this phenomenon arises from waves because when the Rayleigh wave travels, it has several frequency content. For example, high frequency content or short wavelength sample top layer. When the frequency content is low, the waves are longer wavelength, it basically covers the deeper layer actually. So we have waves propagating at wide range of frequency. So from that, basically, we can determine indirectly the soil stratification. Addition to that, we can determine also the velocity profile that can be useful for particularly seismic site classification as well as seismic site response analysis. My focus on mainly for site stratification only. So here it's shown that actually, so the relay wave, you can give it just impact, some hammer blows or SPT hammer blow also we can do. So basically this wave has some wave component high frequency, some have low frequency. The high frequency content only covers the shallow depth layer, but the low frequency, otherwise long wave, it covers deeper depth actually. So from this principle, when we have multi-vertical geophones catching these waves, in principle, we can indirectly determine this layer's velocity as well as important that the thickness of the layers actually. That is what we are interested actually. Practically, we are talking about how you can replace the borehole based stratification actually. Here also you can see that actually, this high frequency wave, you can see that it only covers very few, within less than meter depth only. But when we have a higher, larger wavelength, it covers a deeper area actually. So that based on that only we will be arriving this one. Of course, it's all developed by in UT Austin only, Stoke and Nazarene. They have developed actually. Initially, they called that test called spectral analysis of surface wave because basically based on the frequency content we are analyzing the wave. Therefore, it's called spectral analysis of surface wave. Originally, they have used only 2 geophones only. It's vertical geophones actually. Then one vertical source only actually. Originally, it is developed for mainly to determine the quality of the pavement only. Then only they have extended to the geotechnical engineering field. But nowadays, instead of 2 geophones, they are using what they call 8 geophones, 16, 32. Currently, we are buying also 42 channels actually. We have more channels, mean more accurately we can get the layer profile, as well as we can assess the deeper depth also actually. So currently we are using this MASW test, is called multi-channel analysis of surface wave method. Basically both methods are same only, but we have quite large number of geophones actually. So this is what we've shown that actually. So we have, for example, here typically we have 24 geophones is there. Each geophone it has a low frequency geophones. For example, here it's a 4.5 hertz actually. Basically, the important parameter, the distance between the geophone as well as the what you call offset distance between the source to the first geophone actually. So you can see that, of course, when you are doing impact, it generates both body waves and surface waves. Body waves will be eliminated. From 60 channel automatically, we can have a seismograph. These geophones are covered. Of course, when they hammer, it has also some geophone. It is detecting, then through seismograph, all connected to the geophone, we will be automatically storing the data, catching the data actually. Then we are eliminating the body waves, only surface only we are analyzing. So basically, in this method, first we are accessing the field, the multi-channel records actually, commonly called short gathers. Then we are allowing the dispersion pattern analyzing, extracting the dispersion curve we have to plot actually. There is this relation between the velocity and frequency. Then inverting the dispersion curve, we can get only shear velocity profile. And based on only, if you have multiple things, we can get also 2-dimensional profile actually. So particularly now we come to the region for the study. This is the Chennai city actually. This is the 4th largest. You can see Russia somewhere here, Moscow, far away from Kazakhstan, and this is southern India. 4th largest city in India actually. It spreads over about 9 kilometer length and extend about 9 kilometers. Of course, it's a moderate seismicity only, but according to us, it's zone 5. You can see surrounded by India. Of course, we are close to, our state is close to the Sri Lanka, very only maybe 20, 30 kilometers. We have basically with 1 hour flying time, we can reach Sri Lanka also actually. And of course, well connected to the Middle East, to Singapore, direct flight to New York as well as London also is there. It's a well connected place. And now, of course, we have largest beach, one of the largest beach in Asia. It's called Marina Beach, is in Chennai only. And we have very historical monuments, is mostly constructed by the time during British period, as well as during earlier our kingdoms, Indian kingdoms period also there. You can see the modern flyovers also there. This is in our campus, it is in the forest actually. You can see the deers and black bucks. So one of the deer is recent photo is crossing the road actually in the night time. And about the geology it's primarily consisting of the crystalline metamorphic rock as well as sandstone deposit. And of course we have a unconsolidated alluvium because we have 2 rivers actually. One is the Adaya River. This is close to our institute, close to the international airport. Another one is the Kuam River actually. Of course, through the river, the soil is transported. Therefore, the transported soil is unconsolidated actually. Therefore, we have the soil conditions widely varies in the city. From, for example, this is the south side. We may have rock at 4 or 5 meters. But if you go to the north side, the rock will be 40 meters. But average will be the rock, bedrock will be about 20 to 30 meters. Like Professor Chin told in South Korea, 20 meters. But here in this city, we have mainly from 20 to 40 meters, the rock is varies. That's why only the pile foundations are adapted actually. Particularly multi-story buildings and heavily loaded structures actually. And we currently, our institute involved in geophysical surveys, particularly by using the MSW test. We involved for tunneling metro projects actually to confirm mainly the borehole data actually. This data will supplement to the borehole data. Of course, it's not replacing, it's supplementing the borehole data. Our area studies mainly focused on the seismic site classification and development of the site period. We have published papers in started 2016, but the studies are over 2010 and 15 actually. One of the paper published in Geotechnical and Geological Engineering 2010. Here, what we have done, the test was carried out. That is the first time in Chennai we have done this test about 30 sites, and also we have collected sample, done also some of the laboratory tests to determine the shear velocity, like Bender element test we have done. And actually, all the sites we have also additional borehole data plus standard penetration data. So therefore, from 200 data used, we have developed a correlation between the shear velocity with the SPT value actually. For all soils, for sand as well as clay, we have developed, it is published in this journal, you can find more details. Based on that, we have developed what we call seismic site classification as per the NEHRB system actually. Zone A mean is a purely rock, we don't have rock. We have zone B, you see the blue, it is northern part, southern part of the city. Then we have C, very dense and shallow bedrock. But the major part of the city, we have only stiff soil actually, varies actually. The D is classification. So based on this site classification, we have concluded that in mostly the short building only mostly vulnerable to the earthquake actually. One single story or double story building in the southern part. The remaining part, mostly 3 to 6 story buildings are vulnerable to the, in case of any earthquake, in case of any occurrence of the earthquake actually. So now after that we are involved mainly for seismic site characterization. For that only we have collected, we have done various tests. But nowadays we are doing, our purpose is mainly to have more detail about the site profile actually. Not that we are not much interested in shear velocity profile. Mainly we are interested in the site profile actually. For that we will be taking this particular presentation. I'm taking, we have large number of there's a large number of sites we have done only for this current presentation. I'm taking 3 typical sites. One is Thomas Nagar, Oliman Coil. This one is a clay, predominantly clay stratum, predominantly sandy stratum. Other one is very solid of the rocky stratum actually. Okay, there are in the city, some areas it is there, but this particular place is slightly away from the city actually. See here we have used a 24 channel seismic recorder, makeup geometrics USA. The geophone has 4.5 hertz actually. The hammer, what we are using to 10 gauge sledgehammer. Spacing we are adapting 1 meter to 1.5 meter. Source offset, that is distance from the first geophone to the source, 3 to 6 meter. Of course, this all we have to select. This is what it called. It's not automatically we can get the all record. We have to change the spacing as well as offset distance to get a good wave data actually. For processing, we have used Surface software. Currently, a large number of software available for international market to analyze this wave propagation, this S-wave velocity data. So this basically you see that 3 parameters it is there actually. One is basically what we are talking about it is distance from this is the source where giving impact to the first geophone, that is called offset distance. Then distance between geophone, then the overall distance actually. These are the 3 distance will be there. If you look at that one more clear, one is the D, other one is X. The L is from first geophone to the last geophone. Of course, the optimum important task here is how to select these dimensions actually, D, X and L. For that, there are various recommendations is there. The spacing between should be less than 0.1 times the maximum depth of interest. Some case we are interested only study for example, pavement purpose. We may be interested to know only what within 5 meters only. But for our building purpose, we may interest up to rock actually. So depending on the desert maximum depth of investigation, we can arrive this distance. Similarly, the offset distance should be more than half of the maximum depth. Then the overall length of the geophone array should be more than the depth of investigation. So these are things. There are later studies also, there are various recommendations, but anyway, we cannot blindly follow this one. Depending on our site condition, we have to select these 3 parameters. I already told the parameters which we are used for our case actually. So this is the predominantly clay stratum actually. You can see that the top layers 200 less than it can be 150. It's a relatively soft medium. It can be loose and relatively loose to medium sand or soft clay to medium stiff clay. But below that, you can see that up to 15 meters, we are getting the velocity increases from 250 to 450 meters. Then we are getting 800 meters is basically very dense or placed close to the weathered rock, followed by maybe a rock actually. Here you can see the same site only. This is the SPT profile. Okay. Mostly, for example, this is the low SPT value. Then SPT value increases, then finally go to the chord. So more or less the same profile we are predicting here actually. And also additional to that, we are also compared the earlier correlation proposed by our group itself, how it works actually. The empirical result is basically, this is the blue color is the test result. The black dotted one is the empirical one. It's giving, but however, it's so not exactly matching, particularly for very stiff soils actually. Similarly, for sandy type of soil also, we can see that typically up to 5 meters we are getting low velocity. Then about 60 meters we are increasing the velocity, then followed by a hard strata actually. Here also the SPT profile and serial velocity profile matching. Here this empirical correlation predicts very well up to 14 meters actually. This is predominantly rocky strata, solid depth only about 1.2 meters, weathered rock only, therefore its velocity, very stiff material, 350 meters. Then it's increasing 400 to 800, some same site, we may get also 1200 per second actually. But here if you look at weathered rock layer, SPT, we cannot do that actually. Therefore, we cannot, assuming some SPT 100 we have predicted, but it will not work out actually. Obviously, for weather track, we don't have any correlation. It may not work. I think nowhere it is proposed also. I couldn't find any literature where this correlation available for weather track. Of course, there are some of people critical to the SPT test in the weather track actually. So with this, I will complete my presentation. So what we are is, for the subsoil profile obtained this test actually reasonably matched with that, but however, particularly is reasonably matched with the borehole data. It will give additional information. The correlation, existing correlation developed by our group only, it can be used for certain type of soil, but not for all the type of soil actually. Particularly for weather track site, the correlation may not be applicable or it may not be adequate. So future research should be more on the how to develop relationship between whether SPT or some other parameter with the shear velocity for weather track, and more focus, our focus is how to distinguish. Of course, the hammer blows energy may not adequate. Further, we may go for high energy impact systems that are commercial level to go very deeper depth, so that even behind weather rock, we can reach to the hard rock actually. Thank you.
Thank you, Professor Bumi, for your very interesting presentations, especially related to the Chennai region, India. So please, some questions or comments from our participants, our invited speakers also. So my questions is, if no questions, my questions is Professor Bumi. So,
yeah.
So you have many big territory in India, you know, is seismic, especially seismic zone. So each seismic region, for especially Madras or Bombay, Mumbai or Delhi, so each region has some seismic map, some.
Yeah, what we call seismic migration map. They are all developing actually. For Delhi already they have developed maps. For other major 10 cities, they are developing this seismic microzonation maps actually. What we have developed is what we call initial maps, what we call as actually. Full-fledged maps, for example, whole city dividing with the equal grids, and we're doing both borehole data, MSW data, some other geophysical tests. Combining that, they are currently our Ministry of Earth Sciences given contract to the several institution plus private agency to gather the data. Finally, that the data will be utilized to develop microzonation maps, like what they are doing in Japan or in New Zealand. I know earlier in Russia also the type of map developed. So currently it's in the progress actually. It's a major project. It's currently going on in the it's major cities actually, for major cities.
So thank you very much. Thank you. So I want to also inform our audience that Professor Bumi graduated in Moscow. So he graduated in Moscow University of name of Patrice Lumumba, of name of this University of Friendship. But anyway, Professor Diduch, I understand, and gave for Professor Bumi very good knowledge. So he know very well Russian, our standard, and also Indian standard, and also West standard, and as well in the US. So unfortunately, you cannot this time come to Moscow. Next time, maybe you come. So today, Minister of Construction made some report. So I told about one professor who graduated in Russia cannot come there from India, Professor Bumi. So thank you for your good presentation.
Thank you for all those who listened to my presentation. Thank you all. See you soon.
Thank you. So anyway, so next our speaker, our invited lecture, Professor Yoshinori Ivasaki. So Professor Yoshinori Ivasaki, President of Geo Research Institute in Osaka. So he is also graduated and received in the bachelor degree in Kyoto University and master degree of geotechnical engineering in the University of Berkeley, United States, San Francisco, and also received doctor engineering degree in Kyoto University and also doctor PhD degree in Kazakhstan, Karaganda Industrial State University. So today, Professor Yoshinori Ivasaki also chair of ITC 19 Asian Technical Committee of Historical Sites, and he is now make presentation related with active fault in Osaka area, especially in Osaka region, included Osaka Bay. So please, Professor Yoshinori Ivasaki. So he not here?
Oh, he's there.
No? Okay, maybe...
His name is here. He's sleeping.
okay, maybe he has some problem because maybe he not come to Osaka. I will be late to show his video. Anyway, we move to another presenter. So another presenter will be Professor Victor Kalyakin. So Professor Victor Kalyakin is a representative of Delaware University, full professor of Delaware University, New York, and New York City in the United States. And Professor Victor Kalyakin graduated of University Davis and San Francisco, and in bachelor, and he is a master degree in University Berkeley and also in San Francisco, United States, and again University Davis and PhD degree received. So main research topic area related to is computational mechanics and numerical analysis of soil structure interactions. So today his presentation is related to his developing of this numerical analysis in the cohesion soil ground. So please, Professor Victor Kalyakin.
Спасибо.
Пожалуйста.
Thank you, Professor Askar, and welcome to my presentation. In this presentation, I'll be talking about some modeling work we've been doing, summarizing it, but looking ahead at some of the changes we're making in the elastic response. And that doesn't seem very exciting sometimes because plasticity and elastoplasticity and viscoplasticity are of more interest, but the types of simulations we have to do these days require more accuracy in the elastic regime as well. Because we have such a short time for presentations, I cannot give a lot of details, but I want to give an overview of the kind of things we are doing to change existing models and to better assess experimental results that we have seen in the elastic range now. The makeup of my talk is as follows. There'll be a brief overview of the model that we use, some few simulations to show that indeed it's quite accurate, but then focusing on the stress volume change relations as they exist and why they're deficient, and then generalizing that discussion to the place we're going now as far as modifying the elastic response, and then just concluding the talk. Again, with not a lot of time for details because of the short duration of the talk. The model that we use, the generalized bounding surface model, has been developed over many years, and we have been refining the model progressively, and it's definitely has evolved over the last, I would say, 10 years. It's definitely microscopically inspired. It's fully three-dimensional, three-invariant model, time-dependent. It's adaptive in the sense that we have various options in the model, how we model soft cohesive soils. And again, the details are not available here because of lack of time, but I alert you to the two papers listed here as far as references, first for the model and then for the parameters associated with the model. We can assess both isotropically and anisotropically consolidated soils, so we can account for inherent and stress-induced anisotropy. And this is a technique that we developed with my former student Andras Liao, and we feel very confident, and I'll show some results briefly today about the anisotropy that we compute. We can do an associative or non-associative flow rule. The latter is necessary for modeling material softening, and I'll show a couple of examples of that, of very soft clays. Again, this is in the relatively large strain regime, not the elasticity part. So I will contrast the two as we go forward. The basic premise of the model, which sets it apart from other classes of models, is that progressive inelastic response depending on the distance, in this case shown as delta, the distance from the actual stress point here, this is in hypothetical biaxial stress space, to the suitably defined point on the outer surface, the so-called bounding surface. So you have gradual plasticity, unlike standard elastoplastic models. You may have a region of true elastic response, but in between that region and the outer surface is gradual plasticity, and this is well suited for soft materials such as cohesive soils. The actual model is three-dimensional, as I mentioned. This is the bounding surface. That hypothetical circle that you saw is now a three-dimensional surface. It is a function of three invariants, and it changes with the load angle, the angular distance in the octahedral plane. This is the plastic potential surface and the failure surface associated with it, likewise three-dimensional and changing with the load angle. And these expressions were developed over time and shown to be quite accurate. For example, if I go to the very simplest form of the model, this is the form with the isotropic state of stress and the associative flow rule, and I look at Cambridge clay. This is a kaolin done by Roth and Loudon, various over-consolidation ratios from 1 to 6.5, relatively soft clay. You can see that this is just stress paths. Because of lack of time, I'll show only this, but this is just the usual stress paths. You can see quite good simulation. The red lines being model simulations, the discrete points, of course, experimental data. And the question is what does this bounding surface concept buy you? Well, we know that if we use classical elastoplasticity, especially over-consolidated soils tend to be overly stiff. And so we simulate the same soil with our model, but making it look like an elastoplastic model, and that's the difference. This is where modified cam clay or soft soil model in Plaxis, et cetera, would be. Much too stiff, especially as you get higher and higher over consolidation, even though in the normally consolidated region you can see differences, elastoplastic formulations being too stiff, whereas the bounding surface, that gradual plasticity, of course, gives you much better simulations over the broad range of over-consolidation ratios. Now, that was a simple soil. Let's look at some more complex soils. Boston blue clay is a famous soil in the Boston region in the eastern part of the US. It's marine silty clay, and it exhibits strain softening. And you can see here, this is deviator stress versus axial strain. The softening response, and to capture that accurately, we need non-associative flow rules, not only an isotropic form of the model, but non-associative flow rule. You can see that the stress paths are not beginning on the hydrostatic axis, they're beginning somewhere up here. Clearly anisotropic, but also strain softening. You can see this very pronounced softening response, and to do the proper simulation requires non-associative flow rule. So certainly the model has very strong capabilities, especially at larger strains. This is Taipei silty clay, a little bit closer to the work of on the Pacific Rim. Also very soft soil. You can see it again is anisotropic. It's not associated requirements to capture the strain softening. You can see some of the early part of the response is not captured, especially in extension. And that is sort of what has motivated us to look at the elasticity that I'm talking about today. But certainly the larger strain response is quite reasonable, and the softening is captured. This drop in the stress with strain is certainly captured by the most complex form of our model. Now, again, the interest in the elasticity response is motivated by recent, no, not so recent actually, maybe over the last 10, 15 years, recent work on tunneling. And in tunneling, small strains are very important. This has been shown by numerous authors. And so the definition of your elastic response assumes greater importance in such applications, let's say tunneling, also and certainly in foundation work. So we look at the existing relationship between stress and volume change. And volume change is done, of course, through void ratio, E. And here is the classic critical state concept of E log P curves. P is the mean normal effective stress. And the slope of the virgin consolidation line is the negative of lambda, and the slope of the swell recompression line being the negative of kappa, a classical kind of approximation. And we use the same type of approximation in our work. Traditionally, we decompose the rate of void ratio into elastic and inelastic parts, the inelastic being both plastic and viscoplastic. From the previous plot, we know that the change in the elastic piece is related to the change in the first stress invariant, I, which is 3 times P, through kappa. In the limit, when we take derivatives, we have, of course, the log entering, and then if we take rates, we have that this is just equal to negative kappa I dot over I. If we then relate this to volume change, which we want to do, we want to relate stress to strain. So volume change, the volumetric strain, of course, is the related to the elastic portion of the void ratio as shown. That's a classic small strain assumption. And then we substitute instead of the elastic piece, of course, this expression here. And we set up the volumetric increment, the elastic volumetric increment, then in terms of I and I dot and void ratio. And then we look at, for isotropic elasticity, the relationship between I and I dot and the volumetric elastic piece through the bulk modulus, of course. Substituting the expression from the previous page gives us this kind of relationship where we rewrite things in terms of void ratio and solve for the bulk modulus and get the classic kind of example or relationship between bulk modulus and I, or this may be in critical state cell mechanics written as 3P, and the initial void ratio and kappa. Okay, so this is very classic, or you can rewrite this as kappa related to the bulk modulus and I. It doesn't matter either way. So this would be the elastic response, the bulk modulus. Of course, it's a function of I. It's a proportional directly to I. And for the second elastic parameter, because this is isotropic elasticity, it's typically Poisson's ratio, a constant Poisson's ratio, or a constant shear modulus. That's pretty simple. That's very straightforward in critical state soil mechanics formulations. And we use the same to relate stress and volume change. Now, this has to change because the more accurate representation of elastic response requires that we revisit the experimental work and then change this approach that we use in the model. Professor Bumi just talked about field testing involving determination of shear wave velocities and so forth. This is traditionally the way moduli in an elastic range have been determined, both actually in the lab and in the field. In the lab, resonant column tests beginning in the 1930s, developed in, by the way, Japan, were expanded, forming a way to determine elastic moduli through torsional vibrations. This evolved into cyclic torsional shear tests, and now cyclic and monotonic, I should add, axisymmetric triaxial tests, typically with Bender elements. This is work that was especially pronounced in the 1990s and 2000s in Japan, to better understand how the parameters varied, the elastic parameters, in very small strains. And so it's now realized that the expression I had before, where a modulus, such as the bulk modulus, is proportional to I, is really not consistent with experimental findings. These findings show that moduli, typically shear modulus, is a function of many things, but most importantly, the three things I show here in the bulleted items: state of stress. Obviously, the state of stress has an effect on the modulus, we know that. Density, though, void ratio, is typically used to quantify density, and certainly stress history. And so you see expressions such as the famous expressions by Hardin and co-workers beginning in the 60s and 70s, where I have G, the elastic shear modulus, is a function of the I, that's the same mean effective stress invariant, the first invariant, raised to a power, N, but also involving void ratio in the numerator to a power and in the denominator by itself. So you have a variation of the moduli, not like we showed the bulk modules increasing with I, but because n is roughly a half, it actually decreases with increased stress to better match experimental results. So this is a complete rethinking of the elastic response as we see it in the model. So what do? Well, we assume, for example, under isotropy, that G expression that I just showed and a constant Poisson's ratio, and we compute then the bulk modulus by the elastic relationship between K and G through Poisson's ratio. But instead of G, of course, we now have the variable formulation in terms of I to the n, and A is another model parameter, and it certainly becomes a more complex expression. But we recall that we can relate kappa, the previous kappa, to bulk modulus, shown this way, except that it's not the original critical state parameter kappa, but what I call kappa tilde. It's an equivalent swell recompression index, where K is this K now, with a variable G, that again is much better suited to experimental data and therefore would be much more accurate at small strains. So this is the approach that we are using now to recast elasticity as we have seen it before. It's clearly nonlinear elasticity, but now rewriting it in terms of more rational formulations, not necessarily the standard critical state kappa type line. Conclusions, because of lack of time. So the model we use, the generalized bounding surface model, is a very adaptive approach for simulating saturated cohesive soil response, both isotropic and isotropic formulations, associative, non-associative flow rules. And again, the adaptive is necessary in especially large simulations because not all aspects of, let's say, soil deposit need to have the most complex form of the model. So it can be adaptive, it can be very simple, it can be very complex, it depends on the needs. We realized though, with time, especially with new applications such as tunneling and foundation work, that the elastic moduli must be generalized. And that's what I tried to briefly, very briefly, summarize today. I showed you the case for isotropic elasticity, how we can take expressions such as the Harden moduli and modify the way we do our elastic response through kappa, but now it's a generalized kappa, this kappa tilde, and those type of expressions will find their way into the isotropic hardening of the model. I didn't have time to talk about that, but that will also be affected, of course. And the approach will give more accurate response in the elastic range, the smaller strains. The higher strain values I showed will be unaffected really, but it's the lower strains that we are concerned about. And time precluded me from mentioning the extension to transversely isotropic elastic idealizations. You can see the cartoon here of this typical transverse isotropic idealization. These planes of isotropy, the x2, x3 planes, and the direction normal to that having a different property. These, of course, have 5 elastic parameters, and it's a very kind of evolving area still about how we quantify them. This can also be treated. I did not cover that, but you can calculate, again, this tilde kappa for transversely isotropic cases with the 5 parameters and apply the model to those when, of course, you're doing an isotropic response. With that, I'll say спасибо за внимание. Thank you very much for listening. I hope I did not go over my time. And I'll stop sharing.
Yeah, thank you, Viktor Nikolaevich. Very interesting, especially deep equations.
No.
Deep mathematics.
Only 10 minutes, you know.
This is very good information, especially for presentation, especially for young generation, not only for adult people. So please, some questions or some comments. So no questions from auditorium for participants. So my questions is Viktor Nikolaevich. My questions is for you make some especially for you showed for us a special model of calculations and also for demonstrations and also for some maybe some example, maybe some applications. So what applications you can use of this model?
Yeah, well, we have applied the model as it developed laboratory results like I showed, but we've also used this to model, for example, a caisson infilled island in the Beaufort Sea, the Canadian Beaufort Sea, sitting on a soft foundation. We've done simulations with Professor Ling, actually, in Columbia, and student Ching of excavations in both Boston, that Boston blue clay I showed, as well as in Taipei, the Taipei silty clay. We've done actual excavations. We've done other simulations which involved preloading and consolidation of an actual site in Philadelphia, actually, where you've been, near the airport. And other field applications where we try and apply this where possible to large boundary value problems. So not only have we done laboratory simulations, but also field work as well.
So anyway, thank you for, but this is, you told about the excavations, it is deep excavations, right?
Deep, yes, basements, multiple basements for, especially in Taipei, they were building a very large building, multiple basements, and this was simulated quite well. Very complex, very soft soil. I showed the Taipei silty clay very briefly today. Very soft soil, exhibiting softening with strains. So this was done, yes.
So we have also the soft soil interactions with deep excavations, also St. Petersburg and also Baltic country in the former Soviet Union. So we have interesting regarding of these deep excavations now. Thank you. Thank you. So thank you, Professor. So now we move to Professor Ivasaki. So Professor Ivasaki will be demonstrated of a movie because he has maybe some transportation, some not problem and no time, maybe some typhoon or some tsunami come to Japan. So he sent immediately for us prepared video because you know Japanese very quick work, especially some people sleeping, but Japanese not sleeping there. So he prepared a good video. So now we will try show. Okay.
But he was there. Oh, he is there. Sound.
Можно, да? Можно? Голос побольше можно сделать? А здесь мой забрать можно, да? Мой, чтобы убрать мое. Где-то нельзя. Все уже.
Askar, we cannot hear. We cannot hear. Askar, we cannot hear. We cannot hear.
Who?
We cannot hear his voice.
You not listen voice?
Yeah, no.
Его не слышно, Аскар.
Сейчас можно, да? Just a moment. Голос не слышно. Его голос не слышно. У меня слышен. Это у него не слышно. И участника. Понял, да, участники? Пошло? Что нужно?
Topological expression of upland and lowland.
Сейчас слышно? Слышно сейчас?
Да, да,
As you can see,
да.
Okay.
the topology.
Sorry, thank you.
This is the
Спасибо. Сейчас у нас не то сделали, да?
in this area. This is upland, and here lowland, and in between the slope and underground we found faults. So this is the downgoing, this is upgoing movements. Here, this is the hill. And this boring data is just north and south, this direction. You can see the in the upper formation is horizontally deposited. This is alluvium MA13, and MA12 is here, disappeared. The lower deposit MA11, this is the upcoming and disappears. And in somehow these area geological professors are saying this might be the faults. So these faults is something like this direction. So after the Kobe earthquake, the Osaka city asked me to make some fault survey. So I just make seismic diffraction survey here. This is north and south. This is the upland here. The result is here. This is the base rock, and in the surface area layers are deformed like this. This corresponds to this surface boring data. This side is just subsided, and this is the heaving up. So the fault displacement, the base rock is from the surface 1.5 kilometer, very deep, and the fault displacement is something like 0.5 kilometer, 500 meters. But at the surface, not like this abrupt displacement, rather than just continuous deformation. And the width of this fracture is 0.5 to 0.7 kilometers. Those are the boring data plotted points. And in the western side, this is a subsidence site, and in the eastern side, upheaving site. So this is the upheave, and these are the subsided. And here, these are the faulting area we call fracture belt. The responsible structures, if these faults activated, this is before the earthquake, fault movement, the structure just stands upright position. However, when the faults move, this area just deforms and the structure just incline. And the inclination angle is about 2 to 3 bar by 100. This is good enough, strong inclination to make some damage to the structure. Conclusions I made. Faults are usually associated with topological surface expressions, difference in ground heights. However, the fault movements are covered with flat surface and only discovered by seismic survey or boring database system. In Osaka, a fault and fracture system has been identified and warning has been made from geoengineering to the society. Thank you for your attention. Yoshi Iwasaki, Geo Research Institute, Osaka.
Thank you very much, Ивасаки-сенсей. Так, можно, да? Можно, да? Минуточку. Молодой человек.
Thank you.
Да, thank you. So, можно, да? Заново надо повторить, возвратиться. Все. Так. So, thank you. So, unfortunately, Professor Ivasaki cannot participate, so we cannot give questions, but you can send questions to me or to him directly. Da. So he will reply. You know, in Japan, many earthquake, some tsunami, so they come and influence to our great Professor Ivasaki. Da. But Iwasaki-sensei preparation, good video, is good solution. So anyway, next presenter will be Professor Dervin Chang. So Professor Dervin Chang from Tamkang University, Taipei, Taiwan. He graduated also in Taiwan, and he obtained a PhD degree in the United States. So Professor Dervin Chang is one of very active member of Chinese Taipei Geotechnical Society. He plays the role of chairman of last 16th Asian Regional Conference in Taipei last year. It's very good organized, a very good team, and good results. So anyway, Professor Dervin Chan also specialist for piling foundations, and today his topic related with some numeric analysis of settlement of piling foundations, and during time of interactions of clay, and during time of vertical loading. So please, Professor Dervin Chan.
Okay. Just a minute. Can you see it?
Yes.
Okay. Okay. Thank you very much, Professor Askar, for inviting me to this program. The lecture I'm going to present is the title of the presentation is Approximate Computer-Based Analysis for Pile Raft Foundation in Clays Under the Vertical Load. Because in Taiwan, Professor Victor just say that Taipei, clay. In Taipei, we have silty clay. So in the beginning of this, try to developing this analysis, I was thinking about the performance of the foundation on the side of the clays, especially the soft clays. In Taiwan, when we define the soft clay, it means that the shear wave velocity is under the 180 meter per second. And as you can see later on, I will show you in the parametric studies I conduct we will try to assuming the clays with the shear wave velocity around 120 up to 180s. I'm the first author of this paper, and Mr. Hong is my master student because I'm collaborating with Professor Askar for a long time. So I invited Professor Askar to be my co-author in this paper. I'm very pleased and honored to join this program. Okay, in this study, we will try to develop a very simplified analysis for the 3D parallel foundation using the finite difference method. I will try to explain to you how we did that. This is the methodology we use, discrete foundation, okay? This is a 3D parallel foundation. We assuming the RAF can be simplified, can be simulated by 2D plate, thin plate, especially thin plate. This is what we concerned in the beginning. And also the piles can be simulated by the discrete segment, of the elements. And as maybe some of you know Professor Poulos, he suggests that the design of analysis of the parallel foundation can have three kind of different category of the solution. The first one is, of course, the simplified one, which is called the analytical method. The second one is the approximate computer-based method. And the third one is called the rigorous computer-based method, which has been known as the finite element method in the modern times. And for the second category, I think a lot of researchers try to develop this type of solution in the past. And in here, my proposed solution is falling to the second type of category because it is a simplified solution. So, which means it has the potential to, obtain the solution in a much faster way compared to the finite element method. So this is the methodology of the things. As you can see, for the 2D plate, we just use the thin plate theory, and this type of solution has this type of equation has been suggested by Bollis in his very famous textbook. So as you can tell, this is the governing differential equation, and we use the finite difference solution to try to use the finite difference solution to solve this equation. And this is, but in the beginning, I think in most of the textbook, people won't discuss about the boundary, effects. So in this type of solution, I try to introduce, well, this is the finite plate, not the infinity plate. So we must consider the effects of the boundaries. What kind of boundary we consider? We assume the shear and the moments along the boundary is equal to 0, as you can see from here. Then once we derive the things, we will end up with 6 type of equation, but according to the location of the grid point. So totally we will have 25 different equations derived, and this is the form of the things. And this type of things has been introduced or discussed in this paper. And for the as we have the foundation already solved, then we must consider the springs, soil springs. For any type of foundation which have the deflections, the springs underneath the foundation must be, variable. It cannot be assumed as a constant. It's not going to, perform as a rigid type of foundation. So this is what we try to suggest. We use the finite element, try to check the things, backfigure what type of the soil spring, variate underneath the foundation, and then come up with this type of things. We assume this is a polynomial function, and with the normalized things, we can, assume this is a one-dimensional things, and in the different direction they are the same. So once we have different
different directions functions obtained, derived, we can assume this is a two-dimensional, function for the soil springs. So this is what we suggest in my study. And as to the pi, as I already say that, and we assume this is the single pi we derived by the wave equation again, and but it is static, so there's no time dependence of this type of things, only is the static one. Once we have these things, we can also assume this using the finite difference solution to obtain the equivalent pi stiffness of the single pies. So the equivalent pi stiffness is very important in my proposed analysis. And as to the pi-to-pi interaction, what I adopt is I try to use the approximate pi-to-pi interaction factor suggested by Dobry and Gazetas in 1988. And this is the solution regarding to the vertical response of the things. As to the horizontal thing, it's more complicated, but at the time being, we only consider for the vertical response of the thing. And for the comparison, we use the MIDAS program. This is the finite element model we used. It's developed by the MIDAS company. It's a 3D program, and serves about the same. It gives us about the same solution compared to the Plexus program. Okay, for the comparison, we need to validate that our solution. So we focus on the displacement of the foundation. As you can tell, we assume this is a uniform load acting on top of the foundation. The intensity is about 100 kPa, which is equivalent to about 10 floors building. As you can tell, this is elastic because in the beginning, this is in the very, very beginning stage. So everything is assuming linear elastic. And as you can tell, this maximum displacement of the foundation is less than 2 centimeters. And it will be influenced by the shear wave velocity of the things and also the spacing ratio divided by the pile diameter, which is called the SD ratio. And as you can tell, the solid line and the dashed line means the solution between the our proposed analysis and the MIDAS, which means that I think the analysis we propose works quite rationally. And this is the contour plot of the things we compare it to the MIDAS, and with our program we call VPR. This stands for the static in the second version, which including the variation of the soil stiffness underneath the raft, and also the the pi-to-pi interaction between the piles. And this is as the density of the piles increase, you will be able to see more variation of the things. So we try to compare everything, doing some parametric studies. And this is for the displacement, we have the agreeable solution. So further, we want to check the load variation and also the pile stiffness obtained by our solution and also with the MIDAS. As you can tell, with the shear wave velocity vary at in between 120 and 180, and the load sharing from different solution compares very well. However, the pile stiffness, equivalent pile stiffness is a little bit different. As you can tell, this is for the SD equal to 4, which means the density of the pi is the density of the pi is the highest. In this case, we have because the raft dimension of the raft is 26 meter by 26 meter. The thickness of the raft is about 1 meters. So in this case, we have 49 piles the pile diameter is about 1 meter, and we have a 20 meter for the pile length. So in this case, as you can tell, the pile difference, the pile stiffness between these two solutions, varies a little bit, but they are in rational difference. And the pile stiffness is going to vary with the number of the piles. Okay, if the number of the pile is very small, as you can tell, the pile stiffness is going to be large. And the observation we find that is that in contrast with the ridge cap pile group, and for the flexible raft pile raft foundation, you'll be able to find out the center pile. The stiffness of the center pile is a little bit is much bigger, much larger than the corner pile and the edge pile. Okay. However, as the density, as the number of the pile increase, the difference becomes smaller. And also we find out for the large mega type of pile raft foundation, if we plot the displacement ratio with the loading ratio on this type of plot, and this plot was suggested by, I think, Professor Kazenberg and Chowdhury in the design guideline of ISSMG TC212, which was published in 2013, a few years ago. And if you plot the things, plot all the cases, what we have, actually we have more data points here. And we find out most of the case we have was showing that the data points is on the left lower hand side of these things. And as the foundation of the raft tends to be more stiff, or the foundation generally the whole stiffness increase, then the data point is going to shift to up to this region. But I think for the most of the case we obtain here, we find out it's really hard for us to find out the alpha greater than 50%, which means that in our case, the raft, or you can tell that the soil underneath the raft resist a lot of load instead of the soils along the pile to take over this kind of load. This is what we find. However, as the foundation become more rigid, and you will be able to find out that the data point is going to shift toward this region. Okay. So, but this is also very interesting because we find out anyway the discrete type of solution has some blind points, has some limitation because the foundation, as I already say to you, that the foundation stiffness is a big point. However, in the final element analysis, you'll be able to find out if you pick up the stress inside the raft, and if you pick up the stress, on the top element of the pile, there will be a little bit. There will be, there will be a lot of difference between this type of stress. Inside the stress. So you'll be able to image that. You'll be able to think about that the loading carried by the pile on top of the pile element, and the loading carried on the raft, just right on top of the pile is quite different. This is very interesting. We find out, well, the difference is about 3. The ratio is about 3. In most of the case we have. But as you can see, if the soil become more rigid, and the difference is going to drop. Okay. So the conclusion is that for linearly elastic analysis, the computational time of the proposed analysis, this is very surprising. We find out, the final element analysis is very fast if the soil is linear elastic. However, I think for nonlinear or even for the dynamic things, the finite element, the difference between the finite element method and the finite difference method is going to be dramatic. Settlements and loads were found compared with the finite element solution, as I already shown you. The pi stiffness obtained from the soil strength model were found agreeable with the finite element. And there are many, different type of soil model you can choose. You can choose linear elastic soil model from the dynamic analysis of the research, or you can assuming, well, this is very similar to what has been introduced in the textbook, assuming the ultimate strength of the soil. For soil, for instance, Andrean shear strength of the clay, you can use the Andrean shear strength to simulate the friction. Anyway, we find out that the relative displacement between the pi and the soil, in our simulation is always smaller, less than the displacement required for the mobilization of the ultimate strength of the soil. So this is quite reasonable. Even if you assume the Andrean shear strength, you can still do that. Where the displacement to mobilize the soil strength were found much greater than the foundation settlement. Details of the load sharing and the stress inside the foundation element needs further caution since the discrete nature of the finite difference analysis. As to the foundation behavior of omega pi foundation, the center pi will carry more load than other pies, while in conventional group pies, the corner pi takes more load. This is quite different, okay? For flexible foundation, rigid cap, it's a very small size of the cap. As you can tell, the foundation become more rigid. The load sharing mechanism is quite different. The pi stiffness will vary with the S/D ratio. In general, the center pi exert the largest pi stiffness. Its stiffness will decrease with the increase of pi, and it become more consistent with other pi. Reduction of the pi stiffness due to the pi-to-pi interaction was found more significant at the corner pies. The pi-to-pi interaction influence became much smaller when the pi number increased. For the plot of the plot I already showed to you the displacement ratio versus the loading ratio, the mega pi foundation will appear in the lower left region, and the data point of the conventional pi group will move up to the upper region, as I already said that. Thank you very much for your attention.
Thank you, Professor Derwin Chang, for your very interesting presentations. Please, questions or some comments from our participants, audience, or invited speakers?
Professor Askar, can I make comment?
Yes, you can, Professor Bumi. Yes.
Professor Derwin, you made a very excellent presentation.
Thank
We are
you.
in file draft, but more on earthquake response. My question is that how do you select that clay, for example, 120 meters per second? According to you, is it soft clay or medium stiff clay?
Oh, okay. You mean the clay we select? This,
Why you are starting with 120 meters per second?
Yes, because in Taipei, we have in the design code, the seismic design code, we have three type of ground profile, and for the third type, which is the most soft one, okay, in our design code, seismic design code, we assume that the shear wave velocity of the soil is less than 180 meters per second. But as we can tell that most of the clay, most of the soil, their shear wave velocity is always above 100 meters per second. It's really hard for us to find any soil shear wave velocity with the shear wave velocity less than 110 meters per second, perhaps. So in my study, I asked my student to vary the shear wave velocity around 120 up to 180.
What is the typical
The clay soil, we assume it is homogeneous. Yeah,
Okay.
it is not a layer soil. It is a homogeneous soil.
What could be the typical Andrean shear strength of clay?
Okay, I didn't say that because the time limit. We use some empirical formulation suggested by, I forgot the name of the gentleman. This empirical formulation has been, adopted by some researchers in UC Berkeley, I think, and Dickinson. Dickinson. Dr. Dickinson is one of them, and also the empirical formulation was used for Bangkok soil and other area. So we adapt that. And as I recall, the undrained shear strength is range between 32 kPa and up to 76 kPa. Yeah.
In that case, we are not calling as a soft clay.
Soft. Yes.
Usually, we are not calling soft clay. That's why my question: whether in soft clays, whether it's feasible to adapt pile raft concept.
Okay.
In case it's less than 20 kPa.
So the undrained shear strength of the clay up to 76 kPa, maybe, is not that kind of soft, I think. Yeah.
Okay, thank you. Anyway, good work.
Thank you.
Thank you, Professor Derwin, for good presentations. So I think this time is limited. So thank you very much for these presentations. And now we move to next presenter. Next presenter, Dr. PhD students of Ухтинский State Technical University, Mr. Ramon Alfonso Perdomo. So he's from Bogota, Colombia, and also he is also this city, Ukhta is very big city, second city in Komi, our Komi republics included in Russia. So is oil, gas, and also coal mining locations. So please, Ramon. So his topic more related with some engineering operations and some ethics issues of instrumentation optimizations. Please, Ramon.
Thanks for the kind invitation, Professor Askar. Can you hear me?
Yes.
Okay, ladies and gentlemen, good afternoon. I am very happy to be here with you today. And I would like to thank the organizing committee and especially Professor Askar for accepting my report and allow me to present at this important forum. I extend my greetings to the distinguished speakers at the session number 4. So let's get started. The scale of the economic challenge created by the COVID-19 pandemic has not been faced by the world in several decades. To date, the crisis recovery planning has focused primarily in providing historically unprecedented levels of relief that are providing lifeline for individuals and business, trying to stay solvent, to enable the conditions necessary to safely reopen economies while minimizing virus outbreak, a challenge that has been underscored by the recent setback or pause in reopening plans in many countries. The need for recovery plans to overcome the disastrous effects of the pandemic and to expand the productive capacity of cities to contain the widespread impoverishment of the population and the reduction in the quality of life of society is more imminent every day. In complex situations, since ancient times, engineers have had the ability to tip the balance in favor of society, contributing to the improvement of health, human welfare, and building the infrastructure that improve the competitiveness of cities and urban centers. Unfortunately, the public opinion only realized the magnitude of the impact of engineer role when a few disasters occurred. This kind of event plays
Ramon, so we not show only one slide, we show only first slide. We not show another slide.
Yes, this is the introduction.
Okay.
Professor. Okay. This kind of event places us in the eye of the hurricane. Okay? The scope of the challenge of reimagining the economic future of the countries of the world is daunting. It requires thinking quickly about how to generate economic growth and economic recovery at a time when we seem to have reached almost all physical frontiers. Many enthusiastic voices highlight the importance of moving towards digital and environmentally sustainable models. Engineers have quickly incorporated big data, data analysis, and other computational tools to reduce decision-making time while maintaining a traditional approach based on consultation of a voluminous list of regulatory manuals and standards provided by professional organizations. Aligning the new approach of decisions based on analysis of large volumes of data with recurrent consultation of regulations, manual lists of good practices, and the recommendations of organizations, this is not an easy task, especially considering that many gray areas are generated where the engineer or designer must make decisions. Pure data mining without considering the physics involved limits the full understanding of what is really taking place and can lead to incorrect speculations. Under this approach, the questions to do is, where is the room to apply ethics and physics-based analysis? This presentation is driven by the following hypotheses. What approach shall be used to frame engineering data analysis using big data, the traditional one based on industry standards and accepted best practices, or the alternative one based on principles and value using appropriate risk mapping? Sometimes we make good decisions that end up being bad or bad decisions that end up being good failures. Failure comes in two primary forms, through our mistakes and in our fears. As engineers, we must be able to support our decisions with a numerical approach. Consequently, we formulate models that allow us to have a better understanding of the phenomena of the physical world. Any model, whether mathematical or mental, is based on a particular simplified assumptions. Therefore, the results of the model are valid if those assumptions are maintained in reality, physical world. In practical terms, accidents are the result of a combination of undesirable events involving the latent deviations or failures and poor risk management. As engineer has two main activities, diagnosis and design. The diagnosis is based on the empirical and scientific knowledge that can solve the problem, while the design is the development of solutions to the problem to get an optimized result. The engineer's essential function is decision-making. In this activity, he should tend toward the optimization of the system he designs. However, the dynamics of accidents start with a broad decision-making. The scale of values on which established practice is basically reflects the consensus of the profession. Optimization is key to any engineering task. This is because optimization seeks the best way to achieve particular objective or multiple objectives related to that process and the number of resources or other constraints. In particular, the goal of many engineering operations is to reduce costs and deliver predictable results. Results that meet the planned costs, schedules, and functionality. To address the issue to the ethics of big data and process optimization tools, it is necessary to outline some aspects to consider in measuring performance and setting goals in engineering operations. The engineer or designer must be able to establish criteria to organize the data to be analyzed, inquiry about the way they were collected and their characteristics. A transparent attitude must be maintained about who can modify the data values and justifications, identity, privacy, ownership, and reputation. Likewise, a clear methodology for data analysis and correlation must be established. If this is noted, it is possible to reach erroneous conclusions that seems to have a numerical support, but that in reality do not have a support in the physical world. Today, the ethical frameworks of the companies and the criteria of the engineer play a preponderant role. Ethics are highly conceptual and abstract, but the action that you take to design and execute big data innovation in business have very real consequences. Damage to your brand and customer relationship, privacy violations, running afoul of emerging legislation, and the possibility of unintentionally damaging reputation are all potential risks. Ethical issues in modeling are essential issues for all modelers, because all modelers are humans, and all humans must face moral problems. The engineer is not exempt to participate in this debate, where beyond the numerical rationing that support decision-making processes, a framework aligned with the ethical values of the exercise of his profession, the company's ethical values and his own criteria shall be considered. The engineer must be fully aware that errors and inaccuracies in the process of data mining, such as collection, organization, analysis, and use of big data, it can have a great implications. Big data analysis improves the understanding of the physical world in order to perform better simulations. But in order to make viable an analysis with foundations, we must always spot the premise fears. Why are we measuring how we are measured and what we are measured for, before asking ourselves how we can correlate or how we can predict. A mathematical model, it itself has no morals. It is an abstract entity that belongs to the immaterial world. However, such a model reflects an existing or planned existence in the real world. The aim of this modeling is to solve a problem in that world. Digital data strategies are most effective if they support deterministic physics-based decisions rather than statistical or historical practices. Model documentation is necessary to enable other researchers, modelers, to reproduce the outcomes of the model. Indeed, reproduction or its antithesis, falsification, is a basic principle of science. At the beginning of this lecture, I comment there are enthusiastic voices indicating that this conjuncture is adequate to move forward in achieving sustainability goals and embracing the technologies of the fourth industrial revolution. As an engineer, I am convinced that there is always room to improve and encourage innovation in our processes. Certainly, the current moment is propitious to generate a revolution in the way of doing things, but we have to stop and think how we are going to do it. Learning how to recognize ethical decision points and developing the ability to generate explicit ethical discussions provide organizations with an operational capability that will be increasingly important in the future. The ability to demonstrate that business practice honor their values, this is undoubtedly not the only framework that can help. Other organizational capabilities are required to support those business practices. I want to thank to the participants for their attention. Looking forward, I hope the use of an ethical value frameworks will be considered from now and when using big data and data analysis tools. Data and correlations obtaining must always be constrained with the reality of the processes occurring in the physical world. Professor Askar, I give you back the word. I hope I have the time to answer your questions. Thank you. Спасибо большое.
Thank you, Ramon, for very interesting presentations. It was very interesting because, you know, the PhD students participated in our forum, and also from interesting place, Ухта city. So please, some questions or some comments from our participants or our invited speakers. So if no questions, my questions may be some academic questions. Why you usually foreign students study in Moscow or St. Petersburg, but you study in Ухта? Why?
Professor, thanks for the question. It's basically because my specialty is drilling, and I decided move to UCTA because UCTA is a oil city. So I had the opportunity to work with the NIPI Institute that is linked with Gazprom. So I had the opportunity to make research with them. So that's the main reason because I choose UCTA.
Mm-hmm. Okay, interesting. So anyway, it's I wish you in finishing successfully of this university and join with Gazprom. So in future, maybe we join with some conference also again, especially for next year will be big conference Australia. If you contact with me, I will inform you. In 2023 will be big conference also in Astana, Nur-Султан, Kazakhstan. Okay?
Thank you, Professor.
So thank you for your presentations.
Большое спасибо.
So this is... Так, можно, да, молодой человек? Выключить. Ошибка опять, значит. Сложно, да? Так, они меня слышат, да? So, dear colleagues, so now we have last presentation, but some technical problem that come again. Just a moment, please wait 1 minute. Сейчас опять, может, записать нужно? Нет, есть уже. Нет, это теперь как вот открыть его, чтобы вот на полный лист? Вот, пошел, да? Все. А там вот они меня слышат? Да. И видят, да? Ага. Здесь вот это выключить, да? So, dear colleagues, you listen me? My voice?
Yes, yes.
Yes, okay. So, dear colleagues, so my last presentation, I will try very quickly. Geoinformation database for megacities and new capitals. So, I have two my colleagues, Dr. Alibekova and also Dr. PhD Sarsimbayeva. So both of them working together with Geotechnical Institute, and Alibekova also work more related with the Geoinformation database. And Aselia graduated Brunel University in the UK, and she also studied more freezing soils. So this is the contents of my short presentation. I will be very quickly because time already finished our deadline. So I inform about database, especially for Nur-Sultan city, and also inform about in future developing of this geoinformation database for another cities in Kazakhstan. So you can see this our map. Big map, of course, in CIS countries, including Russia, Kazakhstan, and other countries, post-Soviet Union. So you can see this is St. Petersburg, So yesterday I come from St. Petersburg by flight to Moscow, about 1 hour. So you must be know if you go to in Russia, so you haven't 2-week quarantine. Only show you a certificate about you have negative results of COVID-19 test. So, but you not need stay 2 weeks. So it's very good. So anyway, now is a little bit problem in Russia, but anyway, this conference more online, but some part, including Minister of Constructions today, with offline. So you can see this is our country, Kazakhstan, new capital Astana, Nur-Sultan, old capital Almaty. So this is, you can see this is our map already, maybe you know, in Kazakhstan. So we develop our geoinformation database in Astana. So now our group work on the developing of geoinformation database for Almaty. So you can see this Almaty is more mountain area, is Tian Shan mountain area near boundary of China. So this Nur-Sultan is new capital. So before coming to new capital, 1997 was big population, about 120, 150,000. So now its population is 1,500,000. So as you can see, there's many mega project, mega structures. So we invited many foreign architecture, included master plan developed by Kisho Kurakawa architecture. So you already, I told about, we already have geoinformation database after developing of program of geoinformation database from Japan, Kansai area. So we included identify of soil groups beginning from level of 0 until level of 30 meter and more. So our program with control system included general management function, data input control function, data extractions and processing function, and also data padding functions, including different level of soil ground. So this is also very good for each city, because each city already has some city map and city coordinates and characteristics for obtaining of graphic files. So we use of these materials for preparation of geoinformation database, including of soil ground, mechanical and physical properties. So you can see this some creation of geoinformation database using of many coordinates, and also included of AutoCAD program, and also some created of database in Excel. So this data geoinformation data input for including of, again, I told about XY coordinates. So you can see this left side and right side of Ishim River. So including of database which we already provided for Nur-Sultan city. So you can see this zoning of territory of Nur-Sultan by using of different soil ground and different about 8 types, and 8 types included about 7 soil ground and number 3 types for comparison 4. So you can see this new Nur-Sultan city. So Nur-Sultan city included many soil layer. So this zoning map for optimization driving piles lengths, you can see in different locations. So you can see is 7-8 meter, 11-20 meter, but anyway 7 and 8 meter, 8-9 meter is very popular for soil ground of Nur-Sultan. So these results we use especially for driving piles. So we now want also using for continuously for boring piles, and also in future also developing for traditional pile foundations like plate foundations, and also strip foundation, also in isolated foundations. So in the conclusion, I won't say, so geoinformation database very good for preliminary understand of geometrical parameter of piles without engineering geological investigations by using of geoinformation database. So many now is company interested because it's for preliminary understand of especially geometrical parameters of foundations, very important understand geological parameters. So after we decided of these projects, of course, we will make more detailed investigations of soil ground. So this is some reference about our research work. So more research work related to some group. So this group included Alibekova Nurgul, Akajanov, Sumgat, Shakirova Nurgul. So now is new students come, Alpysova, and we work very deeply and long time. So we want to develop for Almaty city and going to West Kazakhstan. So thank you for your listening, and some questions if you have, please. Так, как я остановить-то? Вот? Нет, не останавливает что-то. So,
Mr. Askar?
Yes.
Yeah, you made very good presentation. My question, simple question only. Are you adopting precast piles or driven cast piles? Precast driven piles or driven cast into piles?
Yes, we use, is our driven piles, our driven piles is precast piles. Precast piles and no pre-stressing, usual reinforcing, piles, okay. Because this is piles more popular in CIS countries and also Finland, Baltic, Finland countries. Okay, so thank you very much. So if time limited, so if you, как вот это всех увидеть? Честно? Не получается, да? I want что так размер окна, как тут? Вот нажал 2 раза. Так. So, dear colleagues, deep thanks, especially for in conclusion time. Deep thanks for participations of with presentations of especially invited speakers, and also thank you very much for our participants from Russia, from Kazakhstan, and also from Uzbekistan. We have not so big group, but anyway, about 20-25 persons, about 30 persons. And now I want to see also our Professor Sergei Kudryavtsev from East, from Sakhalin, from Khabarovsk. So there's many professors also participated. And also thank you very much, especially for our students, Ramon. So he is only one student today made presentations. It's very important for him and also for us. So thank you. I hope in future we will be real contact, not online, by offline. This may be better because Moscow is very interesting, especially capital. Russia is very beautiful city. Unfortunately, we cannot participate because it's pandemic. So I wish you to be safe and please keeping especially your health. So see you in future, maybe in Kazakhstan and Russia, maybe also in the next year in Sydney, Australia. Okay. So thank you very much. So
thank you.
До свидания. До свидания. Goodbye. Sayonara.
Thank you.
Okay. Thank you.